Hello, my dear student. Welcome to EPG Pathsala. I am Anchal Srivastava from Department of Physics, Institute of Science, Banaras Hindu University. Today, we are going to discuss about the module titled Magnetic Storage Materials under the paper Nanoscience and Technology 2. After completing this module, my dear student, you are able to learn a few basic processes which shows how the memory storage devices function and what are the inner components of magnetic storage devices. We will also know how a paramagnetic and diamagnetic material can be used to store for storage devices. What are the prevalent magnetic properties of magnetic material such as a spin, magnetic moment, magnetic susceptibility, magnetization and demagnetization, and magnetic coercivity? What are ferro, antiferro, ferrimagnetizations and their distinction due to their different nature of spin and magnetic domains alignment? We will also learn the condition for superparamagnetic material. The topic such as nano devices require an extensive study of nanophysics and nanotechnology. To comprehend the phenomena which occurs at microscopic to nano dimension scale, which is the order of atomic radii, this module will be presenting an outline of fundamental concepts of nanophysics and nanomagnetism, which will facilitate the platform for nano device and its application. It is more important to detect a small magnetic field rather than merely making small storage devices. Advanced in miniaturization of devices has opened up into the massive possibility of high efficiency device like quantum computer. Today, a computer stores discrete unit called bytes and bits, while for quantum computers, qubit are the quantization of memory storage. There are plenty of other astounding possibilities for developing electronic devices and its industries. Through nanophysics and nanotechnology, scientists are trying to harness the properties of magnetism to develop more efficient memory storage devices. The thorough and exhaustive study of magnetism has already been done by various prestigious research institutes across the world, which has revealed that magnetic properties of material is explicitly dependent on the spin property of electrons and on the spin properties of atomic nuclei. It is an electron which is also responsible for the formation of covalent bond in the molecule, and due to electrostatic exchange interaction lead to ferromagnetic state. This ferromagnetic state lead to ferromagnetic properties of material. Here the space function ux and the spin function v of the wave function are given by w is equal to uxv. I am going to talk about magnetic materials. Magnetism is a universal phenomena associated with all materials that are composed of charged particles. The local magnetic field in a magnetically susceptible material is B equal to B applied 1 plus chi m, where B is the applied magnetic field to the material. A very large local magnetic field can result from a small applied field. In this case, this 1 plus chi m is equal to kappa m. It's called the magnetic permeability. Large value of kappa m exceeding 10 to the power 4 are obtained in alloys of nickel and iron, a perm alloys and super alloys, and are fundamentals to the operation of magnetic sensors used in computer, hard disk, and in iPod memory devices. Magnetic materials can respond to the applied magnetic field in two ways. Either they are attracted or repelled. Let us discuss the paramagnetic and diamagnetic materials. The paramagnetism is observed in materials that contains atom or ions with unpaired electrons, whereas paired electronic systems behave as diamagnetic. Diamagnetism can be regarded as originating from the shielding current introduced by the applied magnetic field in the field electron cells. The magnitude of the diamagnetism magnetic response is very small in most of the material except for superconductors. In the uniform magnetic field H, if the magnetic pole of a strength P is placed at an angle theta to another pole and separated by a distance L, then a couple acts on the magnet called a magnetic moment M. The magnetic moment per unit volume is called intensity of magnetization or simply magnetization and is given by capital M is equal to small m by V, where V is the volume of the material. The magnetization per unit magnetic field is called magnetic susceptibility chi, which is defined as chi equal to capital M by capital H. According to the first systematic measurement of the susceptibility of a large number of substances over a wide range of temperature made by French physicist Pierre Curie, chi was found to be independent of temperature for diamagnetic substance, but it varies inversely with the absolute temperature for paramagnetic substances. The intensity of magnetization and susceptibility. As you know, the magnetic susceptibility can be expressed as chi equal to n mu effective 2 by 3 kT, where capital N is the Avogadro number, K is the Boltzmann constant, and mu effective is the effective magnetic moment and is given by mu effective is equal to G bracket J plus 1 bracket close half n mu effective 2 by 3 K is a constant, and therefore the magnetic susceptibility equation can be written as chi equal to C by T. This relation is called Curie's law and C is the Curie constant. The effective magnetic moment mu effective can be calculated from the slope of the plot of 1 by chi versus T, which will be linear for a paramagnetic substances. There are systems which are paramagnetic only above a critical temperature, and below that temperature They undergo a spontaneous ordering of magnetic movements. Based on the type of ordering, such magnetic systems may be classified as ferromagnetic, antiferromagnetic, and ferrimagnetic. Let us talk about ferromagnetic. So, ferromagnetic metal like iron, cobalt, nickel, and compounds of the transition metal ions, rare earth, and actinide elements, their atomic magnetic moment tend to line up in a common direction even in the absence of magnetic field below a certain temperature. This critical temperature is called Curie temperature, which is known as Tc, and ferromagnetic material below Curie temperature exhibit a magnetic moment aligned parallel to each other. All the atomic movement are essentially aligned, giving a net magnetic moment even after a removal of external magnetic field. Let us discuss the magnetic movement. The magnetic movement due to the unpaired electron is regarded as arising from a spin and orbital motion of the electron. The atoms or ions containing unpaired electrons have an overall magnetic movement given by mu j equal to 4s s plus 1 plus l plus 1 half, where s and l are the spin and angular momentum quantum number respectively, and j is the total quantum number resulting from the coupling of the spin and orbital angular momentum. In most cases, especially in the case of transition metal ions, L is negligible and the spin only moment can be calculated as mu s is equal to g s plus 1 half, where g is the gyromagnetic ratio, which is approximately equal to 2. For a single electron, mu s is equal to 1.73 Bohr magnetron, which is given by 1 bm. 1 bm is equal to Eh by 4 pi mc. By putting the value, we will get the constant value in erg per electron, where E and m are charge and mass of the electron respectively. H is the Planck constant and c is the velocity of light. Bohr magnetron is also represented by a symbol of mu b, and 1 mu b is equal to the magnetic moment of an electron in the first Bohr orbit. Commonly, the origin of magnetic moment in the atoms of a material is the motion of electron. In any material, the origin of magnetism lies in the orbital and spin motion of electron and how the electrons are distributed in the orbital and interact with one another. Let us talk the ferro, antiferro, and ferrimagnetizations. Ferromagnetic material are like paramagnets above Tc. Ferromagnetic metals like iron, cobalt, nickel, and compounds of the transition metal ions, rare earth, actinides element, their atomic magnetic movement tend to line up in a common direction when in the absence of magnetic field below a certain temperature. This critical temperature is called QD temperature, and ferromagnetic material below QD temperature exhibit a magnetic moment aligned parallel to each other. All the atomic movements are essentially aligned, giving a net magnetic moment even after the removal of external magnetic field. For antiferromagnetic substances, the individual magnetic movement aligned in a regular pattern with a neighboring movement pointing in the opposite direction. Movement in opposite direction. In the unit cell of the solid, in the case of antiferromagnetism, movement cancel out each other due to anti-parallel alignment below a critical temperature called Néel temperature Tn. Hence, the net magnetization is zero due to the opposite orientation of sublattice magnetization. Antiferromagnetic material are like paramagnet above Tn. Ferrimagnetism is a phenomena where there can be incomplete cancellation of antiferromagnetically arranged movement happens. Ferrimagnetism is also a situation of anti-parallel alignment of moments, but the moments are unequal in magnitudes so that there is a net magnetization. They are like paramagnets above Tn. Ferrimagnetic materials are like ferrites, oxide containing more than one metals, and iron is one of the constituents, and magnetic garnets. It has always been into assumptions that the state of lowest free energy of ferrimagnetic particles or single domain particles have uniform magnetization. Single domain particles are particles with size lesser than a certain critical limit, while in the case of multi-domain particles where particle size are relatively large, there will be non-uniform magnetization associated with them. Any change in quantity of magnetization requires coherence in rotational symmetry of spin of electrons as well as of magnetic nanoparticles domains. This will result in massive increase in corrosivities. Nano-sized magnetic particles exhibit behavior similar to paramagnetism at temperature below Curie or the Néel temperature. Below the Curie or Néel temperature, the thermal energy is sufficient to change the direction of the magnetization of nanoparticles. The individual atom has a negligible magnetic influence. To observe and calculate, after being influenced by an external magnetic field, while the magnetic movement of entire group of nanoparticles tends to align with the externally applied magnetic field. Therefore, after that, these particles will be called as superparamagnetic particles. This is because the property of superparamagnetism only can occur when there are material composed of very small particles. Corrosivity. The corrosivity, also called the magnetic corrosivity, corrosive field or corrosive force, is a measure of the ability of a ferromagnetic material to withstand an external magnetic field without becoming demagnetized. An analogous properties, electric corrosivity, is the ability of a ferroelectric material to withstand an external electric field without becoming depolarized. For ferromagnetic material, the corrosivity is the intensity of the applied magnetic field required to reduce the magnetization of that material to zero after the magnetization of the sample has been driven to saturation. This corrosivity measures the resistance of a ferromagnetic material to becoming demagnetized. Corrosivity is usually measured in oersted or ampere per meter unit and is denoted Hc. It can be measured using BH analyzer or magnetometer. Ferromagnetic material with high corrosivity are called magnetically hard material and are used to make permanent magnets. Material with low corrosivity are said to be magnetically soft. The latter are used in transformer and inductor cores, recording heads, microwave devices, and magnetic shielding. In a nanomagnetic material, the corrosivity is small when the particles are very large. At the starting, the corrosivity increases drastically as the particle size is decreased due to the decreasing size of the domain and their number. After reaching a maximum value of saturation point of the corrosivity, it decreases further as a particle size is decreased. The corrosivity can be zero below certain dimension in nanoscale. Let us discuss the condition for superparamagnetism. Superparamagnetism is a form of magnetism which appears in small ferromagnetic or ferrimagnetic nanoparticles. In sufficiently small nanoparticles, the magnetization can randomly flip directions under the influence of temperature. The typical time between two flips is called the Néel relaxation time. In the absence of an external magnetic field, when the time uses to measure the magnetization of nanoparticle in much longer than the Néel relaxation time, their magnetization appears to be an average zero. They are said to be in the superparamagnetic state. In this state, an external magnetic field is able to magnetize the nanoparticle similarly to a paramagnet. However, their magnetic susceptibility is much larger than paramagnets. Here, few of the properties of supermagnetism are listed below. The first one is the corrosivity, which is zero. The magnetization measured as a function of field at different temperature with superimposed when plotted as function of h by t. In the zero field cooled magnetic measurement, the sample will require cooling to the lowest possible temperature at which a maximum value is observed. This temperature is known as superparamagnetic blocking temperature, TB. The shape of the zero field cooled curve are determined by the particle size, shape, and size distribution. The shape of the curve will be different in two cases, broader in one case and narrow in other, depending on the size distribution of particles and their domain. Let us discuss the magnetic core cell. In case of nanostructure, magnetic material, a significant reduction in saturation magnetization is observed. Therefore, an extremely large magnetic field are usually required for saturation of the magnetization in case of nanomagnetic particle. The possible explanation for the reduced magnetization of nanoparticle is the core cell morphology of nanocrystallites. In this model, a magnetization is originating only from the core of the particle and from predominantly on the surface of each particle. The core cell layer of thickness T, which is a constant, and the magnetization varies with the size by the relation MST is equal to MS1 minus beta by D, where Ms is the saturation magnetization of the bulk, MST is the saturation magnetization of the nanoparticle of diameter d, and B is the constant related to the thickness of the dead layer. Beta is approximately 6T, where T is the thickness. Thus, the saturation magnetization is inversely proportional to the particle size. Hence, we can say that a small particle offers the potential of exhibiting a special effect that are not observed in the bulk material, and great deal of research effort is developed to this field. Surface effect arises due to a spin canting anomaly. Let us discuss the magnetic core cell. Saturation magnetization less than the bulk value may indicate some changes in the magnetic spin structure. Evident for the magnetic spin structure of fine particles, which differs from that of the bulk, is obtained by using mass bar spectroscopic studies. Mass bar spectroscopy techniques provide a direct way of investigating the nano-sized magnetic particles and their spin structure. And for studying non-collinear spin structure, an external magnetic field is applied. This orients the magnetization in the direction of external field. On the reduction of particle size of magnetic material to a nanometer regime, an unusual change in the properties are observed, especially for antiferromagnetic nanomaterial. It is the surface contribution of magnetism which determines the resulting magnetic behavior. It is necessary to be recalled that the net magnetic moment is zero below the Néel temperature in the case of antiferromagnetic materials due to the opposite alignment of the movement of adjacent magnetic ion or atom in lattice. We also know that if size of the magnetic particle will be reduced to nanometer dimension, this will give rise an enhanced net magnetic moment for the nanoparticle, such as in the case of nickel oxide NiO. It is paramagnetic above 250 degrees Celsius and antiferromagnetic below this Néel temperature. When the size of NiO particle is reduced below 10 nanometer, it exhibits a huge increase in their magnetic susceptibility below the Néel temperature and so superparamagnetic behavior at room temperature. So, student, let us summarize what we have learned in this module point by point. So, the point 1, a material may respond to an applied magnetic field in two ways. It may be get attracted or repelled. The second point is the magnetization per unit magnetic field is called magnetic susceptibility and can be written chi is equal to capital M by capital H. We can also write mu j is equal to 4s s plus 1 plus l plus 1 1 by 2, where s and l are the spin and angular moment quantum number respectively, and j is the total angular number respectively, resulting from a coupling of a spin and orbital angular momentum. The spin only moment can be calculated as mu s is equal to g SS plus 1 half. The magnetic susceptibility of the paramagnetic substances as a function of temperature can be expressed as chi is equal to n mu effective 2 by 3 kT, where capital N is the Avogadro number, K is the Boltzmann constant, and U effective is the effective magnetic moment, and is given by mu effective is equal to G Jj plus 1 half to n mu effective 2 by 3 K is a constant, and therefore the magnetic susceptibility equation can be written as chi is equal to C by T. Evidence for the magnetic spin structure of the fine particle, which differs from that of the bulk, obtained by using mass bar spectroscopic studies. And finally, in this model of magnetic core cell, the magnetization is originating only from the core of the particle and from predominantly of the surface of each particle, which is MST is equal to MS1 minus beta by T. This is all about this module. Thank you very much.